Welcome to today's heat transfer lecture. We're going to continue talking about the three modes of heat transfer and their rate equations, just at a very introductory level. Today's topic is radiation, and this is the final mode of heat transfer. So you've seen this slide before if you've watched the other videos, but just as a refresher, we have the three modes of heat transfer being conduction, convection, and radiation. So radiative heat transfer is heat transfer that typically occurs from one surface to another surface. And the rate equation that corresponds with it is called the Stefan-Boltzmann Law. So just a review question, this is the third time with this question because it's important. So what is the driving force for heat transfer? And that is a temperature difference. So for conduction, it was a temperature gradient because in conduction you're typically tracking how heat is moving through a solid. With convection, it's just a delta T, it's an algebraic T1 minus T infinity. And then for radiation, it's going to be a nonlinear term. It's going from surface to surface, and it's actually going to look something like this. The temperature of surface 1 to the fourth power minus the temperature of surface 2 to the fourth power. So the dependence on temperature is certainly very different than in conduction and convection. However, it's still important to know that heat is going to flow from the higher temperature to the lower temperature surface. All right, so just to review again, heat transfer, radiative heat transfer is energy that is emitted by matter due to changes in the electron configurations of its atoms or molecules and is transported as electromagnetic waves or photons. So with radiation, you're actually having a surface, because of its temperature, it's going to be shooting out photons out into space. And then for that heat or that thermal energy to enter another surface, it's got to be intercepted by that other surface. So there is an important distinction between radiation and conduction and convection, whereas radiation doesn't require matter in between these two surfaces. That can be a total vacuum, and you can still get heat coming from here to here because it's by radiation or by these electromagnetic waves that pulse out from a surface to another surface. So let's just try and put some practicality and experience to help you get your head around how radiation works. So I'm sure most of you have stood by a fire before. So if you stand by a fire, you'll notice that you get hot, obviously, but as you get hot, but that heat doesn't come from the air around you. The air around you isn't necessarily getting overly hot. You feel that heat coming to you directly from the flame. So if you were to block that, if you were to put something in between you would actually stop feeling the heat. So radiation, or thermal energy emitted by radiation, works a lot like light. It just happens to be, just like light, thermal radiation is part of the electromagnetic spectrum. It's just coming from a different wavelength than visible light. So if you blocked your view from the fire, you wouldn't be able to see the fire. If you were to block your view from the fire, you also wouldn't be able to feel it because you'd be blocking that thermal radiation. So this is a surface-to-surface phenomenon. If we thought of this fire as a surface and you as a surface, some of that photons and electromagnetic energy is going to be emitted from that fire, and you are going to intercept some of it, which would cause your body to absorb some of that heat to the point that you could physically feel it. And even though there would have to be air for the fire to be burning, the heat transfer doesn't require that air in between. And largely air is mostly transparent to radiation, so even if there were a vacuum between you and the fire, you'd still be able to feel that heat. And this is just the same way that Earth gets heat from the sun. It's 93 million miles of just emptiness, vacuum, and yet heat can still be transferred very effectively from the sun across that 93 million miles all the way out to Earth. Okay, so let's introduce the Stefan-Boltzmann Law. As I've mentioned, the Stefan-Boltzmann Law will tell us about the rate at which heat is transferred from one surface to another. So the surface that's emitting thermal energy is going to do so in proportion to its temperature to the fourth power. I showed you that temperature difference driving force. This is where it originates from. So the Stefan-Boltzmann Law tells us that the emissive power, or the total rate at which energy is being emitted from a surface, is proportional to epsilon Epsilon is a property of the surface called the emissivity of a surface. So a white painted wall is going to have a different emissivity than a rock, and both of those are going to have a different emissivity than a steel surface. So this is a property of the particular surface, will determine largely how much heat is able to be emitted from that surface. So the emissive power is proportional to the emissivity multiplied by this variable sigma. Sigma is just a constant. It's always the same. That's called the Stefan-Boltzmann constant, and it happens to be equal to 5.67 times 10 to the minus 8 with units of watts per meter squared per Kelvin to the fourth. And you'll notice those units come in really handy when you're actually applying this law. So we have the emissive power is proportional to epsilon times sigma times the temperature of the surface to the fourth power. This quantity, sigma times the surface temperature to the fourth power, is also known as the emissive power of a black body. So a black body, one of the assumptions of a black body is that it emits perfectly. So there is nothing else hindering heat transfer except for the temperature itself. We use this epsilon as a nice convenient term as a relative ratio of how much does that surface emit relative to that of a black body. So this is going to be a decimal number between 0 and 1 that tells us, okay, I emit half or 3/4 of what a black body would emit. So epsilon is always going to be between 0 and 1, with 1 being, again, the emissivity of a black body, so a perfect emitter. The best you could do would be to have a black body, or the highest rate of heat transfer you could get by radiation is if you have the surface being a black body. Okay, so let's talk a little bit more about the Stefan-Boltzmann law. So the surface is going to emit thermal energy. So here's a surface. It's going to be emitting this thermal energy with its emissive power of E. The surface may also be losing heat by convection. That's not exactly what we're talking about right now. And again, you remember all those terms from before. So you'll notice on this figure we also have energy can also be intercepted by this surface from elsewhere. It could be coming from another surface up here, which is also emitting. Let's call that E1. And so whatever from there is emitted from this surface, whatever portion of that hits this surface is referred to as G. So G is the energy absorption due to irradiation. Actually, I misspoke. G is the actual irradiation hitting the surface. So that's given in terms of flux in watts per meter squared. So that's what's coming in and hitting our surface, but we have to multiply that by this alpha term. So alpha is referred to as the surface absorptivity, and the product of those two is what is actually absorbed. So some of that energy is going to hit our surface, but not all of it will necessarily be absorbed by the surface. Some of it's going to bounce off and be reflected. And we'll get much more into this in chapters 12 and 13 when we get really in depth into radiation. So for now, we're just trying to define these basic terms and help you get a feel for how radiation works, basically. And there may be some simplistic radiation problems that you'll be solving even before we get to the actual radiation chapters of the book. All right, let's go back to our thought experiment now. So we're standing next to the fire. So as I mentioned, if you got blocked, then that radiation wouldn't necessarily make its way to your actual body, and you wouldn't feel it the same way because there's something blocking you. So only what your body is able to what's actually incident on your body is what your body would have the chance of absorbing. That irradiation would hit your body, and then your body's going to have a certain absorptivity, again a number between 0 and 1, suggesting that your body won't absorb 100% of what hits it, but it'll only absorb a portion of that, and that will be a function of the absorptivity of your skin and of your clothes and of your hair. So radiation, if you haven't had this thought already, radiation from this fire is actually going to be emitted out in all kinds of directions, so that your friends standing next to you, they would also absorb some of that radiation. And a lot of people could take advantage of the warmth from this fire because it's going to be emitting out in all kinds of different directions. So radiation is going to have this, as we're studying radiation heat transfer problems, it's going to have this extra complicating factor where that radiation isn't necessarily being absorbed and emitted just to one surface. It would be hitting multiple surfaces. So the person would, another thing about radiation is that if you noticed, the form of that emissive power equation from the Stefan-Boltzmann law, where E is equal to the emissivity times the Stefan-Boltzmann constant times T to the fourth, this suggests that any surface that has a measurable temperature is going to be emitting energy. So while I've drawn these heat transfer lines going from this flame out to the person, actually the person is going to be emitting some energy back, and the person themselves will also be emitting energy out in all directions. It's just that the person will have a much lower temperature than the fire, so its effect won't be nearly as noticeable as that of the actual flame. But any surface that actually has a measurable non-absolute zero temperature would be emitting radiative energy pretty much at all times. So radiation does get very complicated, where you get into something called a view factor, which says how much of that radiation is actually going from the fire to this person. So it gets really complicated. There's a lot of geometry involved. But first we're going to introduce a little bit of a simplified form of the Stefan-Boltzmann law that'll help us start to solve some simpler problems. So if we have radiation to the surroundings, so we have our surface here, it's going to be emitting radiation. This Q double prime rad is the net radiative heat flux coming from the surface. So that takes into account both E, what the surface is emitting, and G, what is hitting the surface. And if we assume that our surface is going out uniformly to all of its surroundings, that will make dealing with all that, what I called the view factor, a lot easier to deal with. So when we get this particular circumstance, when we have a small object that is completely surrounded by other surfaces at uniform temperature, so if we could approximate our surroundings all occurring at this variable, at this temperature T subscript surroundings, then we can get this much simpler form of this radiation heat transfer relationship. So when we have this special case that our surface is exposed to large surroundings, and those surroundings that are at this uniform temperature T surroundings, then we have the incident irradiation is coming in at G. We're going to assume that's coming in uniformly. We can treat our surroundings, because they're very large, as a black body. So we can assume that that G, what's hitting our surface, is going to be coming as if it were emitted by a black body, sigma times T surroundings to the fourth. We can also make another assumption that if alpha, or the absorptivity of our surface, is equal to epsilon, or the emissivity of our surface, then we can greatly simplify this equation to be, so the net radiative heat transfer from our surface to the surroundings would be what it's emitting minus what it is absorbing. And if we were to plug in, so this TS in parentheses means the emissivity of a black body as a function of the surroundings temperature. So this term would actually be epsilon sigma times TS to the fourth, if we substituted this sigma TS to the fourth being the emissivity, or the emissive power of a black body. So if we do some algebra, we end up with this much simpler equation. The net rate of radiation exchange between the surface and its surroundings is equal to epsilon, or the emissivity of our surface, which we've made the assumption that it's equal to the absorptivity of our surface, times sigma, which is the Stefan-Boltzmann constant, times the temperature of the surface to the fourth power minus the temperature of the surroundings to the fourth power. So this again is given in terms of flux. Notice the double prime there. So if we wanted to get the absolute rate of heat, we would just multiply this flux by the total surface area of our surface, and we'd get this total heat rate form of the equation. Radiation is complex, and I assure you that we'll go into this in much more detail in chapters 12 and 13. So the key takeaway for now is to remember this basic form. When you have a surface that is exchanging heat via radiation to surroundings that are at uniform temperature, and we make the assumption that the absorptivity of the surface is equal to its emissivity, This is called the gray surface assumption. Then we get that the flux by radiation is equal to epsilon times sigma times our surface temperature to the fourth minus the surroundings temperature to the fourth. So just store this equation away. This is the thing that you'll need to remember. And then just keep in mind that radiation will get a lot more complicated with the geometry of very complex systems and a lot of different things, especially when we take away these different black body assumptions. All right, so let's practice applying the Stefan-Boltzmann law to a very simple radiative heat transfer problem. And this problem says, if my roof is at a uniform temperature of 35 degrees C, the effective temperature of the surroundings is 20 degrees C, and the surface area of my roof is 50 meters squared, the emissivity and absorptivity is 0.85, that's of the surface, the roof. How fast is my roof losing heat by radiation to the environment? We want to make sure we do this with the right units. So let's spell this problem out. Let's look at our same house with this nice simple flat roof. Okay, so we're making the assumption that all the surroundings in the environment are going to be at a uniform temperature, T surroundings. So by making that assumption, this roof, by comparison, is a very small object when you consider the whole sky and all of its surroundings. So we can apply this assumption where we use the rate law that the flux, the net radiative heat flux from my roof out to the surroundings is equal to the emissivity of my roof multiplied by the Stefan-Boltzmann constant and my roof temperature to the fourth minus the surrounding temperature to the fourth. So this is a fairly simple plug and chug problem where we want to identify what is Q rad here, and notice that we want the total rate of heat loss and not just the rate of not just the flux, not the rate of heat loss per unit area of my roof. So let's go ahead and plug and chug in here. So we have Q rad is equal to epsilon times sigma times the surface temperature to the fourth minus the surroundings temperature to the fourth, which would give us units of watts per meter squared. So in order to get that into the total rate of heat loss form, or the total heat rate form, we would just multiply this equation by the area. So our total rate of radiative heat exchange is going to be epsilon times sigma times the area times Ts to the fourth minus T surroundings to the fourth. And that would give us units of watts. So let's go ahead and plug and chug. So this is equal to 0.85, which is our emissivity, multiplied by the Stefan-Boltzmann's constant, which is 5.67 times 10 to the minus 8, and it has units of watts per meter squared per Kelvin to the fourth. Now my roof temperature is 35, but if you recall, that is 35 degrees C. So we need to add 273 to convert from degrees C to Kelvin. And we need to convert to absolute temperature before taking this guy to the fourth power. Minus, or the surroundings temperature was 20. Again, that was degrees C, so we need to add 273 here, and we need to make sure we do that before raising it to the fourth power. So that's how our equation looks, and that comes out. Let's double check our units. So the temperature is going to come out to be Kelvin to the fourth. So it's always a good idea to specify the equation first and then use units just as a check. So we get this Kelvin to the fourth canceling out here. Oh, and I'm glad we are doing this unit check because that tells me that I forgot to multiply by our surface area, which was 50 meters squared. So I caught myself from making a big error just by doing this unit check. So that 50 meters squared cancels out here, and we do indeed end up with units of watts. So I'm going to spare you the plugging and chugging. You can type this into your calculator or into an Excel sheet, but we end up with the roof losing 3,926 watts. So my roof would be losing that much heat by radiation to its surroundings. Just as a point of comparison and maybe as a little bit of a sanity check, we did a convection problem, a very similar problem with even the same temperatures, and I believe we got a rate of heat loss of 7,500 watts from convection. So it's good to know that these are at least on the same order of magnitude, which is a nice sanity check that we probably are getting these about right. Okay, so just some notes on radiation. The driving force is the difference in temperatures to the fourth power for each surface. That driving force will basically be the same even as we get into more complex geometries and even as we get away from that black body assumption. Radiation and convection can happen in parallel. So you could have the roof certainly losing heat. You could have a radiative term here and a convective term here. And actually you could have it gaining heat by radiation and losing heat by convection because the driving forces are a little bit different. Convection is going to happen to the based on the air temperature, and radiation is going to happen based on the temperature of all the surroundings. So those could actually be going against each other. You could also get radiation directly from the sun hitting the roof, which would cause it to absorb heat, and probably the reason that it got hotter than its ambient in the first place. So radiation becomes increasingly important at high surface temperatures. So back to that person standing by the fire example, there probably is convection happening where the fire does heat up the air, and then that air would in turn heat you up. But really what you notice is the radiation. You notice that energy being directly absorbed by your body from the fire. So that if someone blocked you from the fire, from your view of the fire, you would immediately notice that you're not absorbing as much heat. Whereas if someone blocked you, you might still be getting a tiny bit of heat by convection, but it wouldn't be as noticeable. And that's because that fire is at such a high temperature that radiation is going to dominate. As T1 gets really, really high, these rates become very large, and you could even neglect convection because it's so small by comparison. So for now, we're just going to consider radiation to surroundings at uniform temperature. So we're just going to be using that Q rad double prime, the flux is equal to epsilon sigma times T1 to the fourth minus T2 to the fourth, which applies when you have an object that is exchanging heat by radiation with its surroundings, and that the object is relatively small compared to the big size of its surroundings. So we'll use this form of the Stefan-Boltzmann law. So for now, this is the form that I want you to remember.